Quantum simulations, a race to decode the universe's hidden rules. Quantum magazine. Recent breakthroughs in both analog and digital quantum computing have sparked a new era of exploration, where scientists aim to replicate the intricate behaviors of the quantum universe, something even the most advanced supercomputers struggle to grasp. At its core, the challenge lies in simulating reality itself. Classical computers can't replicate the world as it is, but quantum computers are designed to model the fundamental laws of nature. In 1981, physicist Richard Feynman proposed that quantum mechanics is the key to understanding the universe, a notion that has fueled decades of research. Today, this vision is nearing reality, with teams racing to build quantum simulators capable of mimicking the behavior of particles and forces at the smallest scales. The quantum frontier. In a lab in Innsbruck, Austria, physicists recently used a quantum computer to simulate a 2D patch of the electromagnetic field. They observed quantum jitter, a phenomenon where particles appear and vanish spontaneously. This mirrors how energy ripples through quantum fields, creating elementary particles. While the electromagnetic field is well understood, the real breakthroughs come when we attempt to simulate processes that defy classical logic, such as the fate of matter under extreme conditions, or the formation of materials with exotic properties like room temperature superconductivity. Physicists like Christine Muschek, a theoretical physicist at the University of Waterloo, emphasize that quantum simulations are not just about accuracy, but about answering fundamental questions. A future quantum simulator could help us solve some of our most pressing scientific mysteries, she says. Similarly, Jad Halame, a physicist at Ludwig Maximilian University of Munich, highlights the potential to map the early universe's dynamics by simulating quantum fields in high resolution. These simulations could reveal how the cosmos evolved from its infancy, offering insights into the origins of galaxies and the nature of dark matter. The tools of the trade. Simulations rely on different approaches. Some use standard quantum computers, while others employ analog systems that mimic physical processes more closely. Digital quantum computers, built from qubits, quantum bits, can perform calculations by manipulating states that exist in multiple forms simultaneously. However, this approach becomes impractical for large-scale systems due to the exponential complexity introduced by entanglement, where particles become linked so that the state of one instantly influences the other, even at vast distances. Analog quantum simulators, on the other hand, model quantum systems using simpler, more tangible constructs. For example, a model airplane in a wind tunnel can mimic the aerodynamics of a real aircraft. This method is less computationally intensive, but offers greater flexibility in capturing the nuances of physical interactions. As physicist Jad Halame notes, there's a fierce competition between analog and digital approaches. What will shape the future of quantum computing? Decoding reality. Quantum simulations are not just about speed, they're about precision. A quantum computer, composed of quantum particles, inherently handles entanglement, which is essential for accurate modeling. Unlike classical computers, which struggle with the infinite complexity of quantum fields, quantum simulators can simulate the dynamic behavior of particles in real time. For instance, a team led by Martin Ringbauer achieved a 2D simulation of the electromagnetic field using calcium-40 ions, a common building block in quantum computers. Their algorithm reduced the number of steps needed by a factor of 10, demonstrating how qudits, quantum digits, can encode more information than qubits. The race to simulate the quantum universe is not just academic. It's critical for advancing technologies like drug discovery, material science, and even understanding the cosmos itself. As researchers scale up these simulations, the gap between theory and practice narrows, bringing us closer to unraveling the mysteries of the universe.